So today I'm going to go over the solutions to the ODE packet which you've received. And in doing so, I'm only going to go over the temperature distribution calculations. I'm not going to go over the heat flux calculations, the MATLAB plots, or the non-dimensionalization. So in problem 1, we're given d squared t dx squared is equal to 0. In the domain, 0 less than or equal to x, which is less than or equal to L. We're given two boundary conditions. T at 0 is equal to t sub 0 at x equals 0, and then we're also given t at L is equal to t sub L at x equals L. Note that this is a second order differential equation, ordinary differential equation. Therefore, you must have two boundary conditions. So to solve this, we're going to start with the original ODE. d squared t dx squared is equal to 0. We're going to integrate this with respect to x. So we're going to use a well-known theorem of calculus, where if you have a function f, which is a function of x, and we're going to integrate the derivative of that, it's equal to f of x plus some constant. And so if we look at our original equation here, we're going to integrate the left-hand side, d squared t dx squared, we can write as d over dx times dt dx, which we're integrating with respect to x, and the right side is going to be 0 dx. And we can say that dt dx is effectively f as a function of x. So therefore, this left side then becomes dt dx plus a constant. The right side also becomes a constant. So what happens then is we can combine the constants. We get our new form here, dt dx is equal to a constant which we'll call c1. And again, what we're going to do is we're going to integrate this new equation with respect to x. The left side now becomes dt dx dx. The right-hand side becomes integral of c1 dx. So the left-hand side again becomes t as a function of x plus some constant, and the right side then becomes c1 times x plus some constant. Again, we're going to combine the constant, and we end up with our general solution. T as a function of x is equal to c1 times x plus c2. So now that we know the general solution, we can solve for the exact solution using our boundary conditions. So at 0, t evaluated at 0 is t0, which is going to be c1 times 0 plus c2. Of course, this goes away, and we end up then getting that c2 then is equal to t0. So we can rewrite our equation then as t as a function of x is going to be c1 times x plus t0. At the other boundary condition, t at L, we get t sub L. It's going to be c1 times L plus t0. We can then solve for c1. So c1 is going to be tL minus t0 over L. Therefore, we get our equation to be t as a function of x is t sub L minus t sub 0 over L times x plus TO. So here is our exact solution. So we can check our result by evaluating our exact solution at the two boundary conditions. So at x equals 0, t evaluated at 0 is equal to TL minus TO over L times 0 plus t sub 0. And of course this all goes away, and we're left then with t evaluated at 0 is equal to t sub 0, which is correct. At L, t evaluated at L is TL minus TO over L times L plus T sub 0. So what this ends up being then is equal to TL minus T sub 0 plus T sub 0. The T sub 0's cancel out. And we're left then with T sub L, which is also correct. So everything appears to be okay with this problem. In the second problem, we're solving the differential equation 1 over R d over dr r dt dr plus q dot over k is equal to 0 in the domain R1 is less than or equal to R, which is less than or equal to R2. This turns out is also a second order differential equation because we have one differential in dt dr in here, and we have a second one out in front of it, d over dr. So the two boundary conditions are t evaluated at R1 is equal to T1, R equals R1, and t evaluated at R2 is equal to T2, R equals R2. So we'll start by solving this by taking the equation itself up top and moving the q dot over k over to the right hand side because they're just a constant. So 1 over R ddr r dt dr is equal to negative q dot over k. So the first thing we want to do is take this equation and multiply it times r to get rid of the 1 over r out front. In doing this, we get d over dr r dt dr equal to negative q dot r over k. Now that we've isolated the derivative d over dr out front, we can then integrate this out with respect to r. And we know that this r dt dr acts like some function f, so then we can integrate it out. This gets us then, on the left side, r dt dr, and the right side is minus q dot r squared over 2k plus a constant c1. So again, we have this r out front, which means we can't do a direct integration, so we need to divide through by r. And what this gives us then is dt dr is minus q dot r over 2k plus c1 over r. Now we can integrate it. Which allows us to get our general solution. T is a function of r. It's minus q dot r squared over 4k plus c1 times the natural log of r plus c2. So now we can start applying our boundary conditions. First, at r equals r1, t evaluated at r1 is equal to t1, which is equal to negative q dot r1 squared over 4k. That's c1 natural log of r1 plus c2. At r equals r2, temperature is equal to T2, which is negative q dot r2 squared over 4k plus c1 natural log r2 plus c2. So from applying the boundary conditions directly, we see we have two equations and two unknowns, c1 and c2. But what we can do then, to make things easy, is we can take the top equation and subtract out the bottom one. And in doing so, we'll be able to get rid of the c2's. So what this gives us then is t1 minus t2 is negative q dot over 4k times r1 squared minus r2 squared plus c1 times the natural log of r1 minus the natural log of r2. And again, the c2's cancel out. Note that this natural log of r1 minus natural log of r2 is the same thing as natural log of r1 over r2. So therefore, we can solve for c1. c1 then is going to be t1 minus t2 plus q dot over 4k times r1 squared minus r2 squared, all divided by the natural log of r1 over r2. So now we can update our differential equation. So t is a function of r, is going to be negative q dot r squared over 4k plus T1 minus T2 plus q dot over 4k r1 squared minus r2 squared over natural log of r1 over r2 times the natural log of r plus c2. So now we have it down to one unknown in c2. Now we can solve for c2 either by evaluating the temperature at r1 or at r2. You're going to get a different answer either way, but the exact solution is valid either way. So what we'll do here is we'll evaluate it at r equals r1. We know we get a temperature of T1 is equal to negative q dot r1 squared over 4k plus all of these terms in the middle, which I'll just copy over. Then we'll add in a subscript 1 to that. So now we can solve for C2. And C2 is going to be T1 plus q dot r1 squared over 4k. Then we're going to have a minus T1 minus T2 plus q dot over 4k r1 squared minus r2 squared over natural log r1 over r2, all that times natural log of r1. So now we have an equation for C2 using the evaluation of our temperature field at r1. We could also do it at r2. In doing so, we get exactly the same equation, except this would be a T2 up front. This r1 would end up being an r2, and instead of an r1 here, it would be an r2. But we'll just go with the equation for C2 that we have above. Now, if you look at this and compare that to the equation up above, you can see that there is this term q dot times r squared over 4k up top, and a q dot r1 squared over 4k on the bottom. So what we can do then is we can combine them, and that'll make our writing a little bit easier since there's a lot of terms. Also, you see we have in the square brackets the same identical terms of constants here, and the only difference is you have a natural log of r up top and a natural log of r1 on the bottom. So we'll combine all these out to get our exact solution. So t as a function of r then is equal to T1 plus q dot r1 squared over 4k. And this is going to equal then to 1 minus r over r1 quantity squared in order to incorporate this term up top here. So that's taken care of, and that's taken care of. We also have the T1 up front. Next, we're going to grab our term in square brackets. So we have a minus and then the term in square brackets times natural log of r1 minus natural log of r, so it'll be natural log of r1 over r. So one final note, if you notice here we have a natural log of r1 over r in this final term. Generally you probably want r to be in the numerator, but the good news is you can flip it by simply making this negative sign up front a positive sign. So therefore this becomes r, and this becomes r sub 1. So for example 3, take the same equation as example 2, 1 over r times d over dr, r dt dr, is q dot over k is equal to 0. But here we change the domain. R is now between 0 and R2. And we're given one boundary condition, t evaluated at R2 is equal to T2. So we have to come up with the second boundary condition, and that second boundary condition must occur at r equals 0 since we already have one at r equals R2. So t at 0 must be a finite number because a temperature field always contains finite temperatures. So if we look at this, we can start with the general solution from example 2. It's minus q dot r squared over 4k plus c1 times natural log of r plus c2. And we can examine then what happens at r equals 0 is that this natural log of r then would go to negative infinity, which is of course not a finite number. Therefore, this whole thing must go away. And we're left then with negative q dot r squared over 4k plus c2. So we can simply just put in our boundary condition at r2, which is t2, which is negative q dot r2 squared over 4k plus c2. Solve for c2, it's t2 plus q dot r2 squared over 4k, which then gives us our exact solution. T as a function of r is equal to t2 plus q dot r2 squared over 4k is 1 minus r over r2 quantity squared. So next, there's example 4. Example 4 uses the equation x dt over dx is equal to some unknown constant c, which is in the domain x1 less than or equal to x, which is less than or equal to x2. We're given two boundary conditions. T at x1 is equal to t1, evaluated at x equals x1, and t at x2 is equal to t2. So this is a nonlinear differential equation because you have an x times a dt dx. However, what we can do is solve this by separation of variables. So we'll keep the dt on the left-hand side and move the x and the dx over to the right-hand side. So dt is equal to the unknown constant c times dx over x. So what we'll do is integrate this for both sides. And notice that you're integrating over different variables on both sides. On the right side, you're going to integrate from x1 to x2, and then you want the corresponding value of t at those two values of x. So t at x1 is equal to t1, and t at x2 is equal to t2. So in doing this, the left side now becomes t2 minus t1, and the right side becomes c times the natural log of x2 minus the natural log of x1, which is of course c times the natural log of x2 over x1. So we can solve for c then as t2 minus t1 over the natural log of x2 over x1. Now let's take this same integral here that we've solved for c with, and we're going to update it to be able to get the actual temperature distribution. What we implicitly did is we applied the boundary conditions both at T1 and T2. But to solve for the temperature distribution, we're going to integrate from x1 now to some unknown position x, which is between x1 and x2. So of course the corresponding temperature at x is T at x. So if we do this, we get T evaluated at x minus T1 is equal to c times the natural log of x divided by x1. But we already know what c is. We've already solved for that. So we can plug that in. And in doing so, we can then finish our problem and get the exact solution. T evaluated at x is T1 plus T2 minus T1 as the natural log of x divided by x1 over the natural log of x2 over x1. For example 5, we're looking at a second order differential equation that looks like this. D squared theta dx squared minus m squared theta is equal to 0 in the domain 0 less than or equal to x less than or equal to L. At x equals 0, theta at 0 is equal to some theta b, and at x equals L, we have the theta dx is equal to 0. In our case here, theta is a temperature difference, T minus some T infinity, where T infinity is a constant, but it's really not that important here. The idea here is we're going to solve for theta, not for T directly. But once we solve for theta, it's very easy just to convert that into temperature just by adding a T infinity on the end. So to tackle this, we're going to propose that theta is of some form, some constant times e to some unknown other constant r times the position x. Therefore, d theta dx is equal to r times c e to the rx. D squared theta dx squared is r squared c e to the rx. So therefore, if we put in our equation here, so for d squared theta dx squared, we get r squared c e to the rx minus m squared times theta, which is c e to the rx, is equal to 0. Which of course we can factor out the c e to the rx. R squared minus m squared equals 0. And the idea is that e to the rx is always going to be a positive quantity. So in order for this to be a non-trivial solution, this goes away. We can then put r in terms of m, which is of course r is equal to plus or minus m. So now we get two possible solutions for r. We have a plus m and a negative m. So we can superpose that to get our general solution. Theta as a function of x is c1e to the mx plus c2e to the minus mx. So now we'll apply our boundary conditions. At x equals 0, we know that c1 times e to the m times 0 plus c2 e to the minus m times 0 is equal to theta sub b. Of course, e to the 0 is just going to be 1. As is e to the negative 0, it's just going to be 1. So therefore, we say c1 plus c2 is equal to theta sub b. At x equals L, we want to calculate d theta dx. So d theta dx is going to be m times c1 e to the mx minus mc2 e to the minus mx. All of this evaluated at L is equal to 0. So we'll do that evaluation. It's going to be m times the quantity c1e to the ml minus c2 e to the minus ml is equal to 0. And again, for the solution to be non-trivial, we must take m away. So therefore, we get our second expression, c1e to the ml minus c2e to the minus ml is equal to 0. So now we have two equations and two unknowns based on our boundary conditions. So what we'll do is we'll copy this first equation that we obtained here, like so. And we'll multiply it times e to the minus ml. So what this ends up giving us then is c1 e to the minus ml plus c2 e to the minus ml is equal to theta sub b e to the minus m sub l. And then we'll add them together. What happens here is that you have a c2 e to the minus ml, the negative sign up front on the top equation, and we have a positive term on the bottom equation, so they just cancel out. So as a result, you get c1 e to the plus ml plus e to the minus ml is equal to theta sub b e to the minus ml, which then allows us to calculate c1 as theta sub b e to the minus ml over e to the plus ml plus e to the minus ml. We can then solve for c sub 2 as theta sub b minus c sub 1 using our boundary condition at theta equals 0. So it's theta sub b minus theta sub b e to the minus ml divided by e to the plus ml plus e to the minus ml. If we take out the theta sub b and use our common denominator, e to the plus ml plus e to the minus ml minus e to the minus ml over e to the plus ml plus e to the minus ml. The e to the minus ml's, of course, cancel out. So we're left then for C2 is equal to theta sub b e to the plus ml over e to the plus ml plus e to the minus ml. Therefore, we can get our exact solution, theta as a function of x, is equal to C1, which is theta sub b e to the minus ml times e to the plus mx over e to the ml plus e to the minus ml, plus C2, which is theta sub b e to the ml e to the minus mx over e to the ml plus e to the minus ml. So we have our exact solution. We can simplify this a little bit by acknowledging the fact that there's a theta b over e to the plus ml plus e to the minus ml for both terms. So we have theta sub b over e to the plus ml plus e to the minus ml times, and we'll combine our exponential terms here, we have e to the minus m times l minus x plus e to the plus m times l minus x. So, in order to finish, I have to introduce you to hyperbolic functions. Hyperbolic functions are as follows. Hyperbolic sine, or sinh, would be 1/2 times e to the plus x minus e to the minus x. There's cosh, or hyperbolic cosine, which is 1/2 e to the x plus e to the minus x. And then there's hyperbolic tangent, or tang, which is simply sinh over cosh. So, if you look at the function here up top that we've gotten for our exact solution, you can see that there's a plus ml and a negative ml in the denominator, and a plus ml minus x and a minus ml minus x in the numerator. So therefore, there's going to be coshes for both the top and the bottom. So our exact solution can be simplified as theta sub b times cosh of ml minus x divided by cosh ml. So for our sixth example, we have a transient problem. d theta dt minus theta over some constant tau. So since we're dealing with a time dependence instead of a spatial dependence, we state that this differential equation is applied for times at or bigger than 0. And since it's a first order differential equation, we only need one initial condition. So say theta at time equals 0 is equal to theta sub I. So this is our initial condition. And again, theta is a temperature difference. In our case here, it's going to be at T minus T infinity. So again, if we solve for theta, then it's very simple to extract out the temperature distribution from that result. So we're going to apply the separation of variables method. So the left side becomes d theta over theta. The right side becomes negative dt over tau. We're going to integrate both sides. If we consider time, we're going to take time starting at 0 out to some time t. And then we're going to have the corresponding values of theta, at 0 being the initial value of theta, out to some theta evaluated at t. So the left side becomes natural log then of theta evaluated at some time t divided by theta I. And the right side becomes minus t over tau. To simplify this out, take the exponential of both sides. Exponential of a natural log gives you the values inside the natural log. So this becomes theta at time t over theta I is equal to the exponential of minus t over tau. And that's your answer.